Hey pre-calc, welcome back. Our objective today is going to be to find a function's inverse and also to test whether two functions are inverses of each other. I've got the checklist on the screen, you know what to do from here. Alright, so here's an interesting little bar graph that I found a few years ago. So the following chart shows women's preferred age difference between themselves and their mate in various countries. And so letting the countries be the domain and their corresponding preferred years older than self be the range, write this data as a set of ordered pairs, such as, if I do Z for Zambia, comma 4.2, right? And C, comma would be 4.5, Poland would be 3.3, Italy would also be 3.3, and the United States would be 2.5. Okay? So would you say this is a function, yes or no? Yes, and why? Because none of the x's repeat, right? In other words, it would pass the vertical line test because no x's repeat. Okay, so for each input, you have one and only one output, right? For Poland, you've only got 3.3, not Poland is 3.3 and another number, right? However, if we reverse, so let's come up here. So if we reverse f, making the domain of f the new range and the range of f the new domain, then would this new function be a function? Would this new relationship be a function? It wouldn't, right? We would have a problem right there, right? If I switch x and y right there, I would have 3.3 comma p and 3.3 comma I. So now I don't have a function anymore, right? Because 3.3, is it going to p or is it going to I? This is a problem, okay? So what happened was, since our y's did repeat, like this 3.3 did repeat, when we switched, we had a problem. We no longer had a function, right? So when we want to find inverses, and if you remember from Algebra 2, and inverses when you invert or switch your x and y, if I want my new relationship to also be a function, my first function needs to not only pass the vertical line test, but also, what do you think? Also needs to pass the horizontal line test, which is what we call a one-to-one function, okay? So when neither your x's nor your y's repeat. All right. Okay, so let's read a little bit and then I'll let you know what I want you to write down. So a function f is a set of ordered pairs x, y. Then we can undo f by reversing the components of all the ordered pairs. Now the result y comma x may or may not be a function, right, as we just saw earlier. Okay, here's what I would like for you to write down. I'm going to scroll up here so you can see this. And of course, the pause on your screen, can you please copy what I have? So the formal definition of two inverses, f and g, is actually that when you compose them, you get back to your original input, which would be x in this case, okay? The formal way of denoting an inverse is f with a superscript of -1, which is not to be confused by 1 over f of x. The two are not the same. It's very unfortunate that we use the same notation. All right, so I'd like for you to write this top sentence here. If we are switching x and y to get our inverse function, then the domain of f is equal to the what of f inverse? Equal to the range of f inverse, exactly. And vice versa, right? And again, note that f inverse does not mean 1 over f of x in general, okay? Force a pause on your screen. Can you please copy example 1? All right, so let's prove that f and g are inverses. And so to do this, remember that we compose the two. So I'm going to have, let's start with f of g of x, okay? So fog. All right, so we are going to go f, and then g of x is x plus 7 over 4. All right, so now what I'm going to do is I'm going to come to my function f, and anywhere I see an x, which is just here, right, I'm replacing it with x plus 7 over 4. So here's what we have. I run into that 4 first, so I've got 4. Now I've got x, so I'm replacing that with x plus 7 over 4, and I've got a minus 7. All right, so notice here that the 4's are going to cancel, right? And then I've got x plus 7 minus 7, which is indeed x, which is great because that is what we're trying to show, okay, that these functions undo each other. Okay, but we do have to show it the other way around as well. So now let's go g of f of x. So now I'm going to go to g of x and look for any x's. I just see this one. And when I see that x, I'm replacing it with the quantity 4x minus 7. Okay, so that's the first thing I see. So I'm replacing that x with 4x minus 7. Now I still have this plus 7 all over 4. So now notice in the numerator, 4x minus 7 plus 7 is just 4x. You've still got a 4 in the denominator, which reduces to x, which is good news, okay? Now here's what I want you to notice. Take a look at f for me one more time. If you plug in a value for x, what would you do first? You would multiply by 4, right? And then you would subtract 7, okay? Now take a look at g of x. Let's take a look at the order there. If I plug in a number for x there, I would first add 7, and then I would divide by 4. That's the order of operations there, right? So notice that f and g have the opposite operations in the opposite order. That's what causes them to undo one another like this. That's what causes them to be inverses of each other. All right, so we've shown if two functions are inverses of one another, but let's write a formal strategy of actually finding an inverse function, okay? So step 1 is going to be to replace f of x with y, and then step 2 is going to be to actually find the inverse relationship, right? So switch x's and y's. Then we are going to solve for y, so that we can get it into function notation. And the last step is going to be to replace y with this notation of f inverse of x, just to be explicit about what we found, right? Okay, so I'm going to force pause on your screen. Let me jump up here. Can you go ahead and copy example 2 for me? All right, so let's take a look at example 2. Okay, so the first thing we are going to do is going to be to replace f of x with y. So I've got y equals x squared plus 5, right? And now I'm going to go ahead and keep this. Okay, now we're going to switch x's and y's. So I've got x equals y squared plus 5. And now this becomes y is greater than or equal to 0, right? And now I want to solve for y, so let's subtract 5. And then we need to square root, but be careful because when you square root, you do need a plus or minus, right? So I've got plus or minus square root of x minus y, 5, is equal to y, okay? Now this is a problem because now I've got 2 outputs for every input, and the reason, this is why we had this at the beginning, okay? Because if you think about the original function, f of x equals x squared plus 5, it looks like this. Does it pass the vertical line test? Absolutely. Does it pass the horizontal line test? It does not. That's why they said, okay, let's make it pass the horizontal line test. Let's only take the positive branch. Okay, let's only take the right side of that. Okay. Now, if we do that, then our inverse will also be a function, right? So let's take a look. Let's come back here. We had that our y's need to be greater than or equal to 0. Well, if that's the case, I need to have just the positive here, correct? So my final answer, I'm going to have just positive square root of x minus 5. I'm dropping the negative. And I'm going to go ahead and do step 4 here, replace y with f inverse of x. And that's my final answer, okay? Notice if we were to graph square root of x minus 5, that's your standard square root function shifted to the right 5. And notice that these, if you remember again from Algebra 2, these are reflections about the line y equals x, right? Because you switch x's and y's, okay? So again, notice domain of the original is here. X is greater than or equal to 0, which is the range of my new function, the red graph, right? and the range of the original, if you look here, goes from 5 to infinity, and that's the domain of the new function. Force a pause on your screen. Can you please copy example 3 for me, and then we'll do it together. All right, so we want to find the inverse, and it says state the domain of the inverse, including any restrictions inherited from f. So remember, the domain of the inverse is the same as the range of my original function, right? So let's think about my original function f of x before we do anything further. So we've got the standard square root function shifted which way? Left 2, okay? So it looks something like this. Now what is the range of this original function? It goes from y equals 0 to infinity, right? So that's going to be my domain of the new function. Okay, so let's go ahead and apply our strategy here. Let's do the first step together. So we've got y equals square root of x plus 2. Why don't you take it from there and hit continue when you are ready to see the answer. All right, we should have gotten x squared minus 2 for f inverse. Do make sure that you include that x has to be greater than or equal to 0, so that again you're just getting that right-hand side of the parabola. Otherwise, we would not be getting a one-to-one function. In other words, a function that passes the horizontal line test. All right, first pause on your screen. Can you please copy example 4, and then we'll do this one together. Okay, we're back. So first, let's switch f of x to y. Now let's go ahead and find the inverse relation, right, by switching x's and y's. So we've got x is equal to y plus 2 all over y minus 3. And now you just solve for y. So here's kind of where it's like, where do we go from here? Here's what I'm going to recommend. Go ahead and multiply both sides by y minus 3. So this is going to be x times y minus 3. And when I multiply the right-hand side, I just am left with y plus 2, right? Okay, let's go ahead and distribute that x. So I get xy minus 3x equals y plus 2. Now, what am I trying to solve for again? We're trying to solve for y. So let's do this. Here's a really common strategy, algebraic strategy that we use a lot in calculus. Anything that has a y, let's get it on one side. Anything that doesn't have a y, get it on the other side. So let's bring all our y's, in this case, to the left-hand side. Doesn't matter which side you pick. So I'm going to have xy minus y on the left side. And then on the right side, I still have that 2. And I'm going to move this 3x over. So that'll be a plus 3x on the right-hand side. Now the reason we did that is because now you can factor out a y in the left, because both terms have that factor of y. So that leaves me with x, be careful here, minus 1, right, equals 2 plus 3x. So y is equal to 2 plus 3x divided by x minus 1. So that is my final answer for f inverse. And what's our domain here? What can x not be? X cannot be 1, right? Because that would cause a 0 in the denominator. And force another pause on your screen. Can you please copy example 5 and go ahead and graph just f for me first. So you're basically going to take these 3 points and connect them with 2 line segments. So here's what we should get for f. Does it pass the vertical line test? It does indeed. Does it pass the horizontal line test? Yeah, and horizontal, again, if it passes the horizontal line test, we call that function a one-to-one function, or the really fancy word is an injective function. So now go ahead and switch x and y on those 3 points and plot f inverse for me as well. Hit continue when you're ready to check your answer. So here's what we should get for the inverse function. Again, notice, if we do it right, that the original and the inverse should be reflections about the line y equals x, again, as we're switching those x's and y's. All right, you all, that is all I have for you today. I'll see you next time.